Hello there, and welcome to Science for Sleep. Tonight we drift into one of the oldest and most mesmerizing forces on Earth, fire. It is both a destroyer and a creator, a flicker of warmth and a storm of chemistry. Long before cities rose from the ground, before the first words were spoken to describe light or heat, there was fire whispering in the darkness, shaping the course of human destiny. It has lived in our myths, our machines, our stars, and our hearts. Fire is not a thing but a transformation, a living border between what was and what will be. It moves like thought, consumes like time, and glows with the same energy that fuels the sun itself. The same physics that turns a simple log into ash also powers the brilliance of the stars scattered across the night sky. Fire, in essence, is the dance of matter and energy made visible, the poetry of atoms in motion, revealing how deeply connected the smallest spark is to the vast machinery of the cosmos. If you enjoy these quiet journeys through science and wonder, take a moment to breathe, let your eyes grow heavy, and allow the gentle light of fire to warm your thoughts as we begin our exploration. Fire is a chain reaction made visible to the human eye, a process rather than a thing, unfolding at breathtaking speed. Molecules of fuel and oxygen meet, break apart, and recombine, releasing energy in every instant. Each reaction ignites the next, creating a self-sustaining wave of transformation. What appears as a steady flame is in fact millions of chemical events happening every second, bonds breaking, electrons rearranging, energy spilling into the air as heat and light. The flame's motion, its flicker and dance, is shaped by invisible currents of air. Too little fuel, and the chain collapses. Too much, and it flares violently before fading. Yet, whether it's the soft glow of a candle or the raging inferno of a wildfire, the same underlying chemistry governs both. Fire is the visible signature of matter transforming, the purest expression of energy in motion. A flame is a boundary, a delicate interface between unburned air and the hot gases of combustion, where molecules are destroyed and reborn. Within that luminous border, atoms rearrange at astonishing speed, trading partners, breaking bonds, and releasing photons. The light we see is born from particles that exist only for fractions of a second, glowing as they cool and vanish. The color of the flame reveals its temperature and composition: blue, yellow, orange, or white, each hue a story written in heat and chemistry. Convection lifts hot air upward, drawing in oxygen from below, maintaining the cycle of renewal. In this slender, shimmering zone, matter gives up its stored energy, turning the invisible into visible beauty, radiating warmth and life before dissolving into darkness once more. Combustion is not destruction, it is transformation. When something burns, it is not erased but reborn in another form. The atoms of fuel combine with oxygen, creating new molecules such as carbon dioxide and water vapor while releasing the energy that once bound them together. This energy rushes outward as heat, sound, and light, driving the next instant of the reaction. Each molecular collision passes its energy to the next, a microscopic relay that continues until the fuel is gone. Ash is what remains, material that cannot join in the dance. Through combustion, we witness chemistry made visible, the restless rearrangement of matter revealing the hidden energy woven through all things. The same laws that shape a candle's flicker also drive the engines that power our world, the rockets that leave Earth, and the wildfires that renew ecosystems. Every burst of flame is an act of creation as much as it is destruction, showing us the endless cycle of change. The colors of fire tell their own stories. When a substance burns, its atoms release energy in exact amounts that determine what color we perceive. Sodium burns a bright, vibrant yellow. Copper glows green or blue, strontium flares deep crimson. These hues are fingerprints of elements, created as electrons jump between energy levels and release photons of specific wavelengths when they fall back. This principle, known as atomic emission, allows scientists to identify elements from the colors of their flames, a method used in everything from laboratory analysis to the art of fireworks. Each explosion in the night sky is a carefully crafted symphony of chemistry, where metal salts paint the heavens in color. Even in a humble candle, a rainbow hides within the glow, blue at the base where combustion is most complete, yellow above where glowing carbon particles radiate before fading. Each hue marks a step in the story of transformation, atoms surrendering energy as they pass from one form to another. The familiar teardrop shape of a candle flame is a marvel of balance. It seems simple, yet its structure reveals the subtle interplay of chemistry and physics. The hottest part lies just above the wick, where vaporized wax meets oxygen, burning at over 1,000 degrees Celsius. The blue at the base signals perfect combustion, while the orange and yellow above come from cooler carbon particles glowing before they vanish. The wick itself survives because melted wax rises through it, feeding the flame while protecting the fibers from full exposure to heat. If the air shifts or oxygen falters, the flame flickers, smokes, or dies. When balance returns, it steadies again, a quiet engine converting solid wax into invisible gases, warmth, and light. The heat you feel on your skin from a candle's glow is ancient sunlight stored in molecules, now released once again as radiant energy. Blue flames burn hotter than orange ones, signaling a perfect harmony between fuel. In such flames, combustion is complete. No soot remains to glow yellow, and the light comes purely from excited molecules at extremely high temperatures. Blue light carries more energy per photon, meaning the reactions inside are more efficient. This is why gas stoves and torches burn blue. Their air supply is finely tuned to achieve clean, controlled combustion, ideal for cooking, welding, or scientific precision. Orange flames, on the other hand, are the result of incomplete combustion. Tiny carbon particles glow as they cool, painting the flame in warm hues. These particles are the remnants of fuel that didn't fully react. The contrast between blue and orange fire reveals the difference between precision and excess, balance and chaos. A blue flame represents near perfection, fuel transformed entirely into heat, light, and invisible gas, leaving behind nothing but energy. Yet not all flames blaze with fierce heat. Under certain conditions, fire can be cool, almost gentle. These are called cold flames, rare, faintly blue, and often so mild they can briefly touch the skin without causing harm. Found in special chemical environments such as alcohol fires with limited oxygen or low-pressure combustion reactions, cold flames burn at temperatures below 200 degrees Celsius. Their energy is released slowly, steadily, without the violent rush we associate with burning. Scientists study these mysterious flames to understand the earliest stages of combustion and to prevent uncontrolled explosions in engines. Even at such low temperatures, the principle remains the same: atoms trading energy through chemical change. Cold flames remind us that fire is not defined by temperature alone, but by transformation itself, the eternal exchange of energy and matter. Fire, in its essence, can exist almost anywhere if the conditions are right. Although oxygen is the most familiar supporter of combustion, it is not the only one. Elements like fluorine or chlorine can also sustain fire under the proper circumstances. What truly matters is balance, the proportion of fuel and oxidizer, the energy needed to break their bonds, and the stability of the resulting compounds. Too little oxidizer, and the flame starves. Too much, and it devours itself in a flash. In laboratories, scientists have ignited flames in atmospheres of hydrogen fluoride or pure chlorine, each glowing with unique colors and behaviors, some green, some violet, some nearly invisible. Every variation reveals another facet of chemistry's elegance. Fire, in all its forms, from the faintest candle to the heart of a star, is a reminder that transformation is the universe's most fundamental rhythm. The warmth that soothes us, the light that guides us, the energy that drives every living cell, all are echoes of the same principle. Fire shows us that nothing truly ends. It only changes form, passing energy forward in an endless chain of creation. As you listen to the quiet hum of the world, imagine the countless fires burning unseen, in the cores of stars, in the spark of life within your cells, in the memories of sunlight stored in every breath of air. Fire connects us to all that has ever been and all that will ever be. It is the story of change itself, glowing softly in the dark, eternal, restless, and alive. These exotic fires reveal that combustion is a universal language of chemistry, dependent only on the ability of atoms to exchange electrons, a dance of energy and matter that transcends the boundaries of our familiar world. Wherever energy can be released through the breaking and reforming of chemical bonds, fire can emerge, even in environments far removed from the gentle oxygen-rich air that feeds our earthly flames. Fire consumes, but in consuming, it also creates, transforming matter into entirely new forms. It is a process of renewal disguised as destruction. When wood burns, for instance, the cellulose that gives it structure breaks down into gases, ash, and charcoal. Hydrocarbons in the fuel combine with oxygen to form carbon dioxide and water vapor, releasing the stored energy of sunlight once captured through photosynthesis. Every wisp of smoke carries molecules that were once part of something solid and alive, and even the minerals that remain behind in ash are the rearranged ghosts of the original material, altered by heat and exposure. In this way, fire becomes an agent of change, converting complex organic substances into simpler, more stable forms. Nothing truly vanishes. It only shifts into new arrangements of atoms. What was once structure becomes energy, and what was once energy becomes warmth and light. Fire allows matter to write new chapters of itself in the ancient language of chemistry. The crackle of burning wood is not random noise but a physical story being told at the microscopic level. Inside every log, even one that feels dry to the touch, tiny pockets of water are trapped within the fibers. As the heat of the flame reaches these hidden droplets, they expand violently into steam, building pressure until they burst through the surface. Each sharp pop or crack is the sound of those miniature explosions, the wood literally breaking under the stress of its own transformation. Sap and trapped gases join in the symphony, snapping and hissing as they escape into the air. This chorus of sound turns burning into a living soundscape, a reminder that even destruction has its rhythm and voice. As the wood continues to heat, it releases volatile gases that rise to feed the flame, turning solid matter into vaporized fuel. The rhythm of crackling logs is the audible heartbeat of energy returning to the air as heat, light, and sound, the final dialogue of a once living substance completing its journey through transformation. Sparks, too, are tiny worlds of change. When a spark flies from a campfire or from the edge of a grinding wheel, it is a speck of material heated so quickly that it glows incandescently before vaporizing. As it leaves the main flame, oxygen attacks its surface, creating a miniature fireball of oxidation. Though small, these reactions are incredibly hot, sometimes exceeding the melting point of steel, and the brilliant trails they leave are the light of atoms losing electrons and forming oxides in real time. In fireworks, this principle becomes art. Metals like iron, titanium, and aluminum are chosen for their color, heat, and burn time, engineered to create dazzling showers of sparks. But even the simplest campfire spark follows the same rule. Each one is a fragment of fuel, lifted into the air by rising heat, completing its own brief combustion before fading into darkness. Every spark is a microcosm of the larger fire, a self-contained burst of chemistry and beauty that lasts for just a heartbeat. Above every flame, the air itself seems to shimmer and dance, bending light like a mirage. This shimmering is caused by heat altering the density of the surrounding gas. As light passes through layers of air at different temperatures, its path bends slightly, creating waves of distortion that our eyes perceive as motion. The hotter the air, the more pronounced the effect, as heat makes molecules move farther apart, creating layers of differing refractive indices. It is the same phenomenon that makes a road appear wet on a hot day, or makes the horizon in a desert waver in illusion. Scientists use lasers in laboratories to study these rippling air patterns, revealing how heat flows through gases. What looks like a gentle halo of motion is actually the signature of convection, the movement of hot air rising and cooler air descending. It is the visual language of air translating invisible temperature gradients into motion and light. Flames flicker because they are constantly being reshaped by the air that surrounds them. A flame is not a static object but a living balance of chemistry and motion, always adjusting to maintain equilibrium. As hot gases rise, cooler air rushes in to replace them, feeding the reaction with fresh oxygen. This ongoing exchange creates pockets of differing fuel-to-air ratios, causing the flame to pulse and dance. Even the smallest movements in the air, a breath, a breeze, a vibration, can alter the flow of heat and the speed of molecular collisions. In perfectly still environments, such as sealed chambers or microgravity experiments, flames take on an entirely different form, holding steady and spherical without flicker. In space, without convection, they become ghostly orbs of blue fire, burning quietly and evenly. On Earth, however, the constant push and pull of air gives fire its familiar motion, making it breathe like a living thing. Each flicker is the visible heartbeat of balance being lost and regained, an endless dance between order and chaos. Within a candle flame lies one of nature's most beautiful secrets: light born from carbon in its final moments. As wax melts and vaporizes, its molecules split into hydrogen and carbon. The hydrogen burns cleanly, producing heat and water vapor, while the carbon lingers, forming microscopic soot particles. These particles are heated until they glow, radiating the golden yellow light that defines candlelight. As they rise, they are gradually consumed, leaving only invisible gases behind. The candle flame, therefore, is not just fire, it is matter on the edge of vanishing, each particle glowing for the briefest instant before disappearing into the air. The gradient of color, from blue at the base to yellow at the tip, marks the story of combustion from perfect chemical balance to the glowing death of carbon. The beauty of candlelight lies in that fleeting moment of transformation, a quiet celebration of impermanence. The shape of a flame, whether it leans, stretches, or stands tall, is drawn by the speed and direction of the surrounding air. In still air, hot gases rise straight upward, creating the classic teardrop shape. When air moves faster, the flame bends, flickers, or streams sideways. The smooth outline of a steady flame marks the elegant balance between rising warm air and the cooler air rushing in to replace it. But if the airflow becomes turbulent, the flame's form breaks apart into chaotic shapes, waves, curls, and jagged edges. Engineers study these flame geometries to understand combustion efficiency, for every curve and twist reveals how heat and oxygen interact. In zero gravity, where there is no upward flow of hot air, flames become perfect spheres, shaped only by molecular diffusion. Thus, the geometry of fire is not random, it is sculpted by the invisible breath of motion itself, a constant negotiation between chemistry and physics. Even sound is part of fire's language. Every flame produces tiny fluctuations in air pressure, and when combustion happens rapidly, these fluctuations turn into sound waves. The crackle of a campfire, the roar of a furnace, the low hum of a gas flame, each is born from the same phenomenon, expanding gases vibrating the air. In small fires, the sounds are soft, comforting. In large ones, they can become powerful enough to resonate deeply, producing tones that seem almost alive. These pressure waves, known as combustion oscillations, can grow so strong that they shake entire engines or rocket chambers, a reminder that fire's voice can be both beautiful and dangerous. Even a quiet candle hums faintly, though too softly for human ears. Fire speaks through vibration, converting heat into sound, energy into motion, a natural symphony woven through the air itself. At its most extreme, fire becomes plasma, the fourth state of matter, where heat is so intense that atoms themselves begin to fall apart. In the upper regions of a flame, temperatures grow high enough to strip electrons from their atoms, creating a gas of charged particles that can conduct electricity. Though weak in an ordinary candle, this ionization can be measured with sensitive instruments, revealing that even small fires carry traces of plasma, behaving like faint electrical conductors. In lightning, stars, and nuclear fusion, this plasma state dominates, showing that fire and starlight are made of the same substance. Thus, from the crackling of a log to the radiant fury of the sun, fire connects all scales of the cosmos, a single principle of transformation linking the microscopic and the infinite. Every flicker, every spark, every soft shimmer in the air is a reminder that change is the only constant. Fire is matter remembering its energy, energy rediscovering its freedom, and light revealing the invisible work of chemistry. It is destruction only in appearance. In truth, it is creation, the endless rewriting of reality, glowing softly in the dark. Fire, in all its manifestations, is a bridge between chemistry and physics, a vivid reminder that energy and matter are deeply intertwined. It is more than light and heat. It is a process that links the smallest atomic exchanges to the grandest natural forces in the universe. Electric fields, for instance, can bend or stretch a flame, revealing that charged particles exist within it. In plasma torches and lightning, this conductivity becomes so strong it can cut through metal or illuminate the sky, while in a candle flame, it appears as a gentle echo of the same process that powers the sun. The plasma within a flame carries an electrical current softly through the air, connecting burning molecules in an intricate web of motion and light. Fire thus exists at the intersection of matter and energy, a transient state where atoms rearrange in glowing equilibrium. Its behavior changes across environments, particularly under varying levels of gravity. On Earth, gravity pulls cooler air downward as hotter gases rise, creating the flickering dance we recognize as a flame. In reduced gravity, such as on the Moon or Mars, convection slows, and the flame spreads wider and dimmer. In the microgravity of orbit, flames lose their flicker entirely, transforming into perfect spheres that glow evenly in every direction. These spherical flames burn at lower temperatures but with greater chemical efficiency, consuming fuel evenly because the reactions spread uniformly through diffusion rather than being stirred by rising heat. In these silent globes, fire reveals its calm, symmetrical nature, freed from turbulence and gravity's influence. Astronauts aboard the International Space Station have described them as floating stars, quiet, radiant, and hauntingly beautiful. Such flames burn with a dim blue hue, their oxygen delivered slowly by diffusion, and their combustion nearly perfect, so complete that almost no soot forms. These experiments in space show that the familiar flicker of a flame is not an inherent property, but a consequence of gravity sculpting air and heat into motion. Fire's dependence on its environment becomes even more striking when we explore how it behaves under conditions of pure oxygen. In an atmosphere composed entirely of oxygen, flames can lose all visible color, becoming nearly invisible as combustion becomes flawless. The absence of incomplete reactions or unburned carbon particles eliminates the yellow and orange glow typical of ordinary flames. Instead, energy is released primarily as heat and ultraviolet radiation, wavelengths beyond human sight. This form of colorless fire burns with tremendous intensity yet offers no visible warning, making it dangerously deceptive. Because it produces little light, such combustion must be handled under strict safety controls. A single spark can set off explosive reactions. These invisible flames reveal that light itself is not essential to fire, but rather a sign of imperfection, a byproduct of incomplete burning. When chemical reactions reach full efficiency, the process becomes a pure, silent exchange of energy, fire reduced to its most fundamental form. Yet not all flames are gentle or invisible. Some roar with power that challenges our imagination. Metals, often thought of as resistant and stable, can themselves burn when divided finely or exposed to extreme heat. Elements like magnesium, titanium, and aluminum ignite in dazzling displays of white or blue fire, reaching temperatures higher than molten rock. Their combustion releases immense energy, forming stable oxides and producing light so bright it can outshine the midday sun. Once started, these reactions are difficult to extinguish, feeding on oxygen and continuing until all the fuel is consumed. This property is harnessed in welding, flares, and pyrotechnics, but it also makes metal fires in factories or ships extremely dangerous. Even underwater, certain metals can sustain combustion. Reactions involving magnesium or similar elements release enough internal oxygen to keep burning beneath the surface, producing eerie, glowing bubbles of flame beneath the waterline. These phenomena remind us that fire is not confined to air. It can exist anywhere fuel and oxidizer coexist. Combustion, at its core, is the story of electrons moving between atoms, a universal process that transcends the boundaries of earth, air, and water. Nature demonstrates this raw, elemental power most dramatically in lightning. A bolt of lightning can heat the air to about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. In that brief instant, electric energy rips through the atmosphere, stripping electrons from atoms and transforming the air into plasma. The sudden expansion of this superheated air generates a shockwave that we hear as thunder, while the light we see is the glowing path of ionized gas cooling rapidly. The channel left behind, only a few centimeters wide, becomes a luminous filament connecting sky and ground, its brightness vanishing as quickly as it appeared. The energy released in that moment fuses, melts, and vaporizes everything in its path, sometimes even transforming sand into glass. When lightning strikes sandy ground, the silica particles fuse together into delicate, hollow tubes known as fulgurites, natural sculptures that trace the path of the electric current. Each fulgurite is unique, branching unpredictably as it plunges into the soil, preserving in glass the record of a single instant of unimaginable energy. Scientists study them to understand the thermal and electrical properties of lightning, while collectors prize them for their fragile beauty, a glimpse of the sky's power crystallized in earth. The spectacle of lightning transforming sand into glass mirrors the violence and artistry of human industry, which uses controlled fire to create similar wonders more slowly. But in nature's version, the entire process takes less than a second. A flash of energy, a roar of thunder, and where there was once sand, there now lies glass, a silent reminder that fire can manifest even in air itself, when electrical fields become powerful enough to tear atoms apart. The power that arcs across the sky during a thunderstorm is a cousin to the plasma in a candle flame, vastly magnified and compressed in time. Not all extraordinary fires belong to storms or stars. Some exist in conditions that seem impossible, like flames that burn underwater. These occur when special chemicals supply their own oxidizer, freeing the reaction from dependence on air. Compounds containing chlorine or fluorine can react with metals such as magnesium or lithium, producing intense heat and light even when submerged. Such underwater flames have practical uses. They illuminate the depths for divers, serve as emergency flares, and enable underwater welding in places where oxygen from the reaction sustains the fire despite the surrounding water. Watching one is surreal. The flames glow diffused through swirling clouds of bubbles, its light trembling like a captured star beneath the surface. This phenomenon shows that fire is ultimately not about where it burns, but about what happens within matter itself, the rearrangement of atoms releasing stored energy as light and heat. Among the strangest substances known to humans is white phosphorus, a material so unstable that it ignites spontaneously at room temperature. Its atoms form a tightly packed, strained structure that seeks to release energy by bonding with oxygen. When exposed to air, white phosphorus begins to glow faintly, a ghostly green luminescence known as chemiluminescence, before bursting into bright yellow flames that emit dense clouds of phosphorus pentoxide smoke. Because it burns so easily, it must be stored under water or inert gas to prevent accidental ignition. Its volatility has made it both useful and dangerous, employed in tracer ammunition, flares, and incendiary devices, yet capable of self-ignition without spark or flame. White phosphorus reminds us that combustion need not wait for external heat. Sometimes, the instability of matter itself is enough to drive fire into being. Even more surreal are the blue fires of Indonesia's volcanic landscapes. On the slopes of Kawah Ijen in Java, streams of molten sulfur ignite when exposed to air, burning at over 360 degrees Celsius and releasing electric blue flames that shimmer across the crater at night. During the day, the flames are invisible, but as darkness falls, the mountain glows with otherworldly rivers of cobalt light. The phenomenon occurs as sulfur gases escape from volcanic vents and catch fire upon contact with oxygen, creating a spectacle that blurs the line between beauty and danger. Miners once worked among these glowing flows to collect solidified sulfur, walking through the luminous haze. The blue color comes from the combustion of sulfur dioxide, which emits light in a different spectrum than ordinary flames, giving the illusion of liquid fire streaming down the rocks. It is a living illustration of how elemental chemistry can produce art beyond human imagination, a reminder that the earth itself is a furnace of transformation, where heat, gas, and minerals combine to paint the night sky in blue fire. Whether in the quiet flicker of a candle, the searing heat of a lightning bolt, or the ghostly glow of volcanic sulfur, fire speaks the same language, the dance of atoms exchanging energy. From the invisible flames of pure oxygen to the violent brilliance of burning metals and the calm symmetry of zero-gravity fire, each manifestation reveals a different facet of a single truth. Combustion is a universal dialogue between matter and motion. It connects the chemistry of a matchstick to the physics of the sun. It forges glass, powers engines, lights our homes, and shapes planets. Fire is not a thing but a process, a fleeting balance between destruction and creation, chaos and order. It glows because of imperfection, it flickers because of gravity, and it exists because the universe itself is built upon the restless exchange of energy. From the still flames that hover like stars in orbit to the blue infernos of volcanic craters, fire shows us that even the most familiar phenomenon is, at heart, a cosmic mystery, a dance of light born from the invisible heartbeat of matter. The blue fire that burns on the volcanic slopes of Indonesia is among the most haunting and mesmerizing spectacles on Earth, a vivid reminder that combustion can take astonishing forms when it emerges from the planet's depths. On the slopes of Kawah Ijen, in the island of Java, molten sulfur seeps out of volcanic vents and ignites when exposed to oxygen, producing an ethereal, electric blue glow that illuminates the night. It is proof that fire is not bound by the familiar colors or conditions we associate with it, that chemistry and heat can conspire to paint the night sky in colors more dreamlike than real. This mysterious glow is born from the meeting of Earth's breath and air's embrace, an ancient alchemy of gas and flame. Yet fire's beauty is not confined to the ground, it burns even in the heavens. Every meteor that streaks across the night sky is a miniature fire in motion, a cosmic ember igniting in the thin upper layers of Earth's atmosphere. When a meteoroid rushes toward our planet, it collides with air molecules at speeds of tens of kilometers per second, and the friction heats its surface to thousands of degrees. The intense energy vaporizes the rock or metal, forming a glowing trail of plasma and molten particles. This fleeting light, what we call a shooting star, is a tiny fire that lasts for only a heartbeat before fading into darkness. Larger meteors, called fireballs, can leave lingering ionized trails that glow in the night sky, painting ephemeral paths through the firmament. The color of these celestial flames depends on the elements they contain. Magnesium burns with a white brilliance, sodium with yellow, nickel with green. Most meteors disintegrate before reaching the ground, but those that survive to become meteorites carry within them the story of fires meeting with speed and air. Even here, in the high reaches of the atmosphere, combustion lives, a process born from cosmic velocity and earthly resistance, as the sky itself becomes a stage for fire's eternal dance. On Earth, fire moves with a different rhythm, one shaped by wind, terrain, and the fuel of life itself. Wildfires can race faster than a human can run, devouring landscapes in waves of orange and gold. Under the right conditions of dry air and powerful wind, flames can travel at more than 20 kilometers an hour, consuming forests and grasslands with terrifying efficiency. The heat of the blaze preheats and dries vegetation ahead of it, preparing it to ignite before the main fire even arrives. Embers, carried aloft by turbulent winds, can ignite spot fires kilometers away, creating a front that spreads unpredictably and unstoppably. The roar of a wildfire is not merely the crackle of burning wood, it is the sound of countless chemical reactions occurring at once, millions of tiny combustions merging into a single vast engine of heat. Scientists study these fires through models and satellites, trying to predict their behavior and protect lives, yet they remain both destroyer and renewer. Though devastating to human life and property, wildfires also play a vital ecological role, clearing dense undergrowth, releasing seeds that sprout only in fire's aftermath, and returning nutrients to the soil. In their destruction lies renewal, in their chaos, balance. Fire, after all, is both life and loss. But when nature's forces align just right, the calm physics of flame gives rise to one of the most awe-inspiring sights imaginable, the fire tornado, or firenado. When a wildfire or industrial blaze grows intense enough, it can create its own rotating column of air. As hot gases rise swiftly, cooler air rushes in from all sides, spinning faster as it narrows, forming a vortex of flame that can tower hundreds of meters into the air. Inside, temperatures can exceed 1,000 degrees Celsius, and winds can rival those of hurricanes. These whirling infernos move unpredictably across the landscape, lifting debris and spreading embers far from their origin. Though they look chaotic, fire tornadoes follow the same laws of physics as ordinary whirlwinds, born from convection, rotation, and heat amplified to extremes. They are nature's sculptures of flame, brief and ferocious, a reminder that air and fire are not separate elements, but partners in a volatile dance. When the wind itself grows fierce enough, even the shape of fire changes. Flames that normally rise toward the sky are forced to bend and crawl along the ground, driven sideways by hurricane-speed gusts. The rushing air feeds oxygen into the fire faster than heat can rise, causing flames to flatten and spread horizontally. This phenomenon can turn hillsides into sheets of moving light, where the fire seems to slither rather than leap. Even rain cannot always quench such flames, as their heat is strong enough to evaporate water instantly. Firefighters must account for this behavior, knowing that in strong winds, flames can leap far ahead of their front line, igniting new ground in seconds. A sideways flame reveals the intimate interplay of motion and heat, how wind can sculpt fire into forms that seem alive, as if the elements themselves were competing to dominate the landscape. At its most extreme, fire becomes an architect of its own weather. In the heart of massive wildfires, the heat rising from the inferno can form towering columns of air that grow into pyrocumulonimbus clouds, thunderclouds born entirely from flame. As the hot gases ascend, they cool and condense moisture, forming storm clouds that stretch kilometers high. Inside these clouds, ash particles and ice crystals collide, generating electric charges that discharge as lightning. This lightning can ignite new fires miles away, perpetuating the storm's reach. Meanwhile, strong inflow winds rush toward the base of the rising column to replace the air that has lifted, feeding the blaze with yet more oxygen. The result is a self-sustaining system, a firestorm that generates wind, thunder, and lightning all from its own energy. Within these vast convective towers, rain and hail can fall through the flames, evaporating before they reach the ground. Temperatures can approach those of volcanoes, and winds can exceed any storm on Earth. In such moments, the boundary between weather and fire dissolves. The blaze becomes an atmospheric engine, shaping the sky above it and writing new patterns of wind and cloud. Not all of fire's greatest heat comes from nature's chaos. Some of it is born from human ingenuity. In controlled environments, flames can reach astonishing temperatures, over 3,000 degrees Celsius. Acetylene torches, used in metalworking, burn so hot that they can melt steel and vaporize glass. Chemical reactions such as the thermite reaction, which combines aluminum powder and iron oxide, produce temperatures exceeding 2,500 degrees, enough to weld railway tracks or cut through thick armor. Magnesium, too, burns with fierce white brilliance, hotter than most volcanic lava. At these extremes, matter itself begins to change character, turning into a fluid of electrons and ions, plasma radiating across the visible spectrum. The air shimmers violently, molecules torn apart by energy. In such flames, chemistry meets physics, and the border between fire and plasma begins to blur. These controlled fires, though dangerous, reveal the very edge of what combustion can be, a glimpse into the heart of creation itself. In scientific laboratories, fire is taken even further, beyond the reach of ordinary chemistry. Inside fusion reactors and plasma research facilities, scientists create bursts of plasma that burn hotter than the core of the sun. Here, hydrogen atoms are confined by powerful magnetic fields until they collide and fuse into helium, releasing vast amounts of energy in the process. The plasma glows with shades of blue and violet, a human-made sun contained within magnetic walls. For fractions of a second, temperatures reach into the millions of degrees, echoing the conditions of the early universe. Despite this unimaginable heat, the energy is tightly confined in small volumes, making it possible to study safely. These experiments aim to unlock the secret of clean, limitless energy, the same power that fuels the stars. In this glowing plasma, matter behaves less like a solid or gas and more like pure energy, an echo of creation itself. Here, fire transcends its earthly meaning and becomes a symbol of cosmic transformation. But even on Earth, without laboratories or volcanoes, fire can still reshape matter in extraordinary ways. When lava flows over the ground, or when lightning strikes a sandy plain, the heat can melt minerals and fuse them into smooth, glassy surfaces. This process, known as vitrification, turns rock into glass, trapping bubbles of gas, streaks of ash, and flashes of light within solidified stone. Such formations tell the story of fire's contact with Earth, of how intense heat can transform even the most enduring materials into something entirely new. Each layer of volcanic glass, each fulgurite formed by lightning, is a frozen instant of transformation, proof that fire is both an artist and a destroyer. It can shape beauty out of ruin, light out of chaos. From blue volcanic flames to cosmic meteor trails, from the gentle shimmer of plasma in laboratories to the roaring infernos of wildfires and firestorms, fire remains the universe's most eloquent expression of energy in motion. It is everywhere, on mountains, in storms, in the skies, and in the hearts of stars. It destroys and creates, terrifies and mesmerizes, teaches and transforms. Every flicker, every spark, every inferno is part of a continuum stretching from the depths of the earth to the farthest reaches of the cosmos. To understand fire is to glimpse the restless heart of nature itself, a force that binds atoms, drives weather, forges worlds, and burns silently in the starlight that falls on our skin. Fire, one of nature's most powerful and transformative forces, has shaped Earth's landscapes, civilizations, and even the evolution of life itself. Ancient hill forts in Scotland and Ireland still bear the marks of this elemental power, walls that have melted together into black glass, evidence of temperatures exceeding 1,500 degrees Celsius. These vitrified fortresses show that fire was not just a destructive weapon but also a transformative one, capable of fusing stone and rewriting the structure of the land itself. In laboratories, scientists replicate these effects with modern furnaces, producing smooth, glossy rock that holds the frozen memory of fire's passage. Each piece tells a story of transformation, solid matter briefly liquefied, only to cool into a permanent testament of heat's fleeting dominance. Fire, in its essence, demonstrates that even Earth's hardest materials can yield to its touch, softening stone and reshaping reality. Yet not all fires are born equal. Some arise in the quiet hum of industry, where molten metal blazes challenge human control. When reactive metals like magnesium, sodium, or aluminum ignite, they unleash heat so intense that water becomes an accomplice rather than a remedy. Instead of quenching the flames, water splits into hydrogen and oxygen, feeding the blaze further in a violent chain reaction. The result can be an explosive eruption of molten droplets, scattered across wide areas. Firefighters combat these infernos not with water but with specialized powders like graphite or sodium chloride, which smother the fire by cutting off oxygen and absorbing excess heat. In factories, molten metal fires remain among the most feared because they can melt through solid floors, devour machinery, and even vaporize concrete under their relentless heat. This reveals a deeper truth about combustion. It is not merely a surface reaction but a chemical dance occurring at the atomic level, one that can transform matter itself. Sometimes, the very things meant to extinguish fire become catalysts for greater destruction. In industrial settings, even the smallest materials can become deadly when exposed to air. Fine aluminum dust, for instance, can form invisible clouds of potential fuel. Each particle's vast surface area invites oxygen to cling to it, creating the perfect conditions for instant combustion. A single spark, perhaps from static electricity or metal friction, can ignite the entire cloud, resulting in a devastating dust explosion. The rapid reaction releases shock waves and temperatures high enough to destroy entire facilities. Such explosions don't just occur with metals. Flour, coal, and other organic powders can react similarly. That's why factories employ strict grounding systems and advanced ventilation to prevent ignition. The danger here lies in geometry as much as chemistry. Tiny, evenly dispersed particles transform the air itself into fuel, erasing the boundary between solid and flame. In that split second of ignition, matter becomes energy, and structure turns to chaos. Even substances we encounter daily can harbor hidden fire. Gasoline, for instance, does not burn as a liquid, it burns as a vapor. When gasoline evaporates, it releases a cloud of flammable gas that can ignite with the faintest spark, sometimes from static electricity alone. A spark from synthetic clothing, a cell phone, or even friction from a gas nozzle can be enough to trigger an explosion. Once ignited, the flame rushes through the vapor cloud and returns to the liquid surface, setting it ablaze. The resulting fire feeds itself through rapid evaporation, consuming its own fumes. The chemistry is deceptively simple yet catastrophic. The smallest, invisible interaction of vapor and spark can unleash immense power. Gasoline fires remind us that danger often hides in what cannot be seen. Fire, however, can manifest even in places where it seems impossible. In frozen environments, certain chemical reactions allow flames to bloom from snow and ice. Elements like sodium and potassium react violently with water, splitting it into hydrogen and oxygen while releasing enough heat to ignite the hydrogen. When these metals meet snow, the result is a startling paradox: flames dancing on ice. This phenomenon reveals that temperature alone doesn't define fire. Rather, it's the energy released when chemical bonds break and reform. Even in the coldest landscapes, energy persists, waiting to be transformed into light and heat. The colors of fire tell their own stories. A copper flame burns green, the result of electrons absorbing energy, leaping to higher energy levels, then releasing light as they return to their original states. This vivid emerald hue is common in fireworks, where copper compounds like copper chloride or acetate are added to produce dazzling displays. Each element's unique atomic structure determines the color it emits, giving us a direct glimpse into the quantum world. Every hue is a fingerprint of an element's inner life, turning the invisible behavior of electrons into visible beauty. Thus, even in something as ephemeral as flame, the secrets of matter and energy reveal themselves through color. Some fires, however, are nearly invisible. Alcohol flames, particularly from methanol or ethanol, can burn so cleanly that they emit almost no visible light. In daylight, these fires are ghost-like, detectable only by their heat or faint blue shimmer in the dark. Such invisibility makes them both useful and dangerous. In laboratories and motorsport environments, where alcohol fuels are common, an unnoticed flame can pose deadly risks. Firefighters and chemists rely on thermal cameras or ultraviolet sensors to detect these unseen blazes. The purity of their combustion, transforming fuel entirely into carbon dioxide and water, means there are no glowing carbon particles to color the fire. They are the quietest, most disciplined forms of combustion, leaving behind no smoke, no soot, and almost no sign of their presence. Yet fire's story does not begin with humans. It predates us by hundreds of millions of years. The first wildfires erupted long before trees existed, when lightning struck mats of dry algae and primitive land plants. These early fires shaped Earth's developing atmosphere, releasing carbon dioxide and other gases that influenced climate and oxygen balance. Fossilized charcoal from nearly 500 million years ago offers evidence of those ancient blazes. As vegetation evolved and oxygen levels rose, fire became an even more powerful shaper of ecosystems. The arrival of trees provided dense, woody fuel, giving rise to massive forest fires that burned with greater intensity and duration. Wildfire thus became part of Earth's evolutionary rhythm, selecting for plants and animals that could resist, recover from, or even depend on fire. Some species developed fireproof bark or seeds that germinate only after exposure to heat, embedding fire into their life cycles. Through destruction, it gave birth to renewal. Lightning, Earth's earliest ignition source, was both destroyer and creator. Long before humans learned to strike flint or spin frictional sparks, lightning set the world ablaze. Each bolt carried millions of volts, striking trees, grasses, and peatlands, transforming entire landscapes in moments. These fires returned nutrients to the soil and opened clearings for new growth. Over time, plants adapted to these cycles, some storing water to survive burns, others spreading seeds in fire's aftermath. In this way, lightning not only forged the planet's early ecosystems, but may also have influenced the chemistry that led to life itself. Some scientists theorize that the reactive compounds formed in these ancient firestorms contributed to organic molecules' development. Every modern lightning flash echoes this ancient connection between sky and earth, reminding us that life itself may have been sparked by flame. Eventually, humans learn not only to fear fire but to control it. Early humans discovered how to preserve embers long before mastering the art of ignition. By covering glowing coals with ash or carrying smoldering sticks, they kept heat alive through cold nights and long migrations. These embers became traveling flames, sources of warmth, protection, and cooked food. Fire allowed humanity to step out of the cycle of daylight, extending activity into the night and providing defense against predators. It became the first tool that truly separated humans from other species, granting control over the environment. From those first embers grew civilization itself, metallurgy, agriculture, pottery, and eventually industry, all born from our mastery of combustion. Through every era, fire has remained both a companion and a threat. It can melt stone, shatter metal, and reshape the very elements of the world. It can hide as a ghost in the daylight, or blaze in green brilliance against the night. It can bloom in the frozen silence of snow or roar through forests as a force of renewal and ruin. From the vitrified hill forts of ancient warriors to the invisible laboratory flames of modern science, fire's essence is constant, a balance between creation and destruction, light and shadow, energy and matter. It is the visible breath of chemistry, the glowing edge of transformation, and the timeless reminder that everything solid can, for a moment, become light. Archaeological evidence reveals that ancient humans learned to maintain and nurture fire long before they mastered the art of creating it. Hearths preserved over thousands of years show that early people tended coals and embers carefully, keeping them alive through nights and seasons. This practice of fire-keeping marked one of the earliest forms of technology, bridging the gap between discovery and mastery. Before humans could strike sparks or kindle flames with tools, they relied on preserving embers, a fragile yet transformative skill that allowed them to migrate, survive, and adapt to new environments. Each glowing coal represented not just warmth and protection, but a captured fragment of the world's raw energy. Within those small fires, humanity carried the first seeds of civilization, a living connection to nature's most powerful force. Charred bones and blackened cave walls tell the story of humans who cooked with fire nearly 2 million years ago, transforming their diet and their destiny. Cooking softened meat, released nutrients, and made plants easier to digest, fueling brain growth and paving the way for modern human evolution. The deliberate use of fire, seen in repeated burn marks, layered ash, and organized hearths, reveals that early humans had moved beyond accidental flames. They had learned to control, contain, and depend upon fire as a partner in survival. What began as a wild, destructive force became a companion and teacher. The light of those ancient flames continues to echo in every candle, lamp, and stove today, connecting us to the first sparks that illuminated the darkness of prehistory. Fire not only gave warmth but also reshaped time itself. Before its discovery, nightfall brought an end to activity. After fire, humanity extended the day beyond sunset. In its glow, people gathered to share food, craft tools, and tell stories long into the night. The flickering rhythm of the flames gave birth to imagination, social connection, and art. Shadows danced across cave walls, inspiring the first symbols, dances, and myths. Around the fire's warmth, fear turned to curiosity, and isolation turned to community. The circle of light became a circle of trust and learning, where the earliest seeds of language and cooperation grew. In the ancient wilderness, the campfire was both fortress and friend. It kept predators at bay, the crackling sound and scent of smoke warning away lions, hyenas, and other nocturnal hunters. Fossilized hearths show that these circles of light were not random. They were deliberate constructions of safety and culture. The boundary between light and darkness marked the line between survival and danger. Within that protective glow, humans rested, dreamed, and began to invent the first tools, songs, and stories born from the calm between flames. The fire gave not only security, but also the space for reflection. It was around those fires that thought deepened, that minds began to weave imagination with reality. Some anthropologists believe language itself may have evolved around campfires. The rhythmic dance of flames gave pattern to speech and flow to storytelling, as gestures mirrored the light and words found meaning through repetition and tone. The campfire became humanity's first stage and classroom, where elders taught and stories preserved memory. Myths, lessons, and histories were carried by voice and flame, passed down across generations as living knowledge. In the firelight, humans learn not just to communicate but to dream together, building shared identity through narrative. This bond between storytelling and fire remains part of us even now. Each spark of creativity, each glowing screen or candlelit conversation echoes those ancient nights when words first found their rhythm in the warmth of flame. Eventually, humans discovered they could make fire themselves. Certain stones, such as flint and pyrite, could strike sparks when hit together. The mastery of spark making marked a turning point in prehistory. When struck with precision, these stones released tiny glowing fragments of metal, sparks that could ignite dry grass or tinder. No longer dependent on lightning or smoldering trees, humans could now summon fire at will. Archaeological finds of flint tools and worn hammerstones reveal how this art became ritual, each spark a symbol of human control over nature's raw energy. Fire making became both a necessity and a sacred act, representing triumph of mind over environment. The first spark struck between stones was more than ignition. It was an awakening of intelligence, an act that separated humanity from the rest of the natural world. The ability to create and control fire reshaped evolution itself. Cooking, once a convenience, became essential to human development. Heat broke down food's toughness, reducing the energy required for digestion and freeing resources for brain growth. The warmth of fire enabled migration into colder regions, allowing humanity to spread across continents once deemed uninhabitable. It sterilized food and water, reducing disease, and its glow drew people together in social unity. Around the hearth, cooperation replaced conflict, and families and tribes were formed. Fire's mastery marked the true dawn of civilization, the moment when humans no longer merely survived but began to shape the world around them. Some of the earliest myths show how deeply fire intertwined with human spirituality. Many cultures saw flame as a living being, a spirit breathing, moving, and consuming with will of its own. Fire was treated as sacred, both feared and worshipped. It was believed to carry messages to the gods through smoke, a bridge between the earthly and divine. Ritual fires were fed with offerings of oil, herbs, or food, tended carefully to ensure they did not die. Across ancient temples and household hearths, flames symbolized purity, transformation, and renewal. They embodied the balance between destruction and creation, reminding people that all life moves through cycles of burning and rebirth. Even today, when we light candles to remember, to pray, or to celebrate, we echo that ancient reverence for fire as a bearer of spirit and connection. Across civilizations, fire also measured time itself. Before mechanical clocks or written calendars, people marked the passage of seasons and celestial events with ritual flames. Great pyres and torches were lit during solstices, equinoxes, and harvests, aligning human life with the rhythms of the cosmos. Fire ceremonies honored the rebirth of the sun, the return of spring, or the waning of the year. Villagers and priests would gather in circles of warmth and shadow, watching sparks drift upward like prayers into the heavens. Through these rites, flame became the visible heart of the universe, a mirror of its endless cycles, ignition, brilliance, and fading into ash. It symbolized not just time but transformation, showing that even in decay, there is renewal. The fire's rhythm became humanity's rhythm, connecting every living being to the great breathing pulse of the cosmos. As knowledge deepened, humans began to refine their relationship with fire even further. They discovered that by burning wood slowly without air, they could create charcoal, a lighter, more concentrated fuel that burned hotter, longer, and cleaner. This innovation, the first engineered fuel, revolutionized early technology. Charcoal allowed the forging of metals, the firing of pottery, and the development of tools and art far more advanced than before. Archaeological evidence shows charcoal pits dating back tens of thousands of years, proof of deliberate experimentation and control over chemistry. Unlike raw wood, charcoal could be stored indefinitely and transported easily, making it a cornerstone of trade and craftsmanship. It powered the first forges and kilns, transforming not just survival but economy and culture. With charcoal, humanity stepped into a new age of creation, where fire became a partner in invention and progress. From the first ember carried carefully through the wilderness to the blazing furnaces of ancient cities, fire has been our most constant companion. It is the thread that ties together survival, imagination, spirituality, and science, a force both wild and tamed, destructive and nurturing. In its glow, humans learned to think, to speak, to believe, and to build. It reshaped our bodies, expanded our horizons, and gave rise to art, technology, and civilization itself. The story of fire is the story of humanity, how we learned to take the raw power of nature and transform it into light, warmth, and knowledge. Every flame we kindle today, whether in a hearth, a lamp, or an electric spark, carries within it the memory of those first fires that burned in the shadows of prehistoric caves, when humanity stood before the dark and, for the first time, made the night its own. Charcoal marked the first moment humanity learned to shape nature's power with purpose, transforming a simple flame into an engineered tool that bridged the gap between the natural and the artificial. It was the beginning of human chemistry, where curiosity and need met the hidden science of heat and transformation. Through controlled burning, people learned to manipulate matter, to purify, strengthen, and reshape it. The mastery of fire made survival in cold and hostile environments possible, allowing migration beyond the warm equatorial regions that once confined early humans. Before fire, the rhythm of life followed the seasons, and winter meant hardship or death. But with fire came warmth, stability, and permanence. Families could endure the cold, cook food, dry hides, and preserve grain. The hearth became the beating heart of the home, a circle of safety and sustenance around which early villages grew. Archaeological remains across Europe and Asia show hearthstones at the center of ancient dwellings, physical proof that flame was the foundation of settlement. The glow of controlled fire not only protected people from predators and darkness but also allowed them to make the wilderness habitable. From that glow spread the first sparks of civilization, expanding human presence into regions once thought unlivable. Fire's creative potential revealed itself again in the accidental discovery of pottery. When clay placed too close to a hearth hardened instead of crumbling, people realized that heat could transform fragile earth into something strong and enduring. This revelation revolutionized daily life. Hardened clay vessels could hold water, cook food, and store harvests safely, turning nomadic survival into settled living. Over time, fire pits evolved into kilns, structures that allowed higher temperatures and consistent results. Pottery soon became both utility and art, its surfaces decorated with carvings, pigments, and symbols that told stories of the people who shaped them. Each fragment of pottery uncovered by archaeologists carries the memory of that first moment, when humans learned that fire could create as well as destroy. It was a perfect harmony of earth, water, and flame, one that changed the rhythm of human existence. The next great leap came when fire reached deep into the rocks themselves. Early people noticed shiny droplets forming in the ashes of their campfires where certain stones had been heated. These were beads of metal, copper or lead melted from the ore beneath. What began as curiosity soon became experimentation. Humans discovered that by building hotter fires using charcoal and controlling airflow, they could coax these metals from stone, shaping them into tools, ornaments, and weapons. This new art, called smelting, gave birth to metallurgy, the science of extracting and refining metals. With it, humanity entered a new era. Stone gave way to copper, copper to bronze, and later iron, each stage reshaping the structure of society. Stronger tools meant better farming, stronger weapons meant larger empires, and beautiful ornaments meant growing cultures of art and trade. Every droplet of molten metal that once gleamed in the ashes of an ancient hearth symbolized not just discovery but transformation, the moment when humanity learned to command the very bones of the earth. Around the same time, another miracle emerged from the meeting of fire and sand. According to legend, ancient traders cooking on a sandy beach with blocks of mineral soda saw the sand melt and fuse into a translucent substance, glass. Whether by accident or design, this marked one of civilization's most transformative discoveries. Glass was unlike anything known before, solid yet transparent, fragile yet eternal. Natural glass had existed for eons, formed by volcanic heat or lightning strikes, but now humans could recreate it deliberately. By blending sand and alkali and exposing it to intense heat, they learned to produce a material that could hold light, magnify vision, and later, shape art and architecture. Ancient glassmakers were revered as alchemists, masters of a secret art that turned earth into clarity. The first glass beads and vessels shimmered like captured sunlight, and from those humble beginnings came windows, lenses, and mirrors, tools that expanded human vision both literally and metaphorically. The ability to shape glass was, in a sense, the ability to shape light itself. The story of fire's partnership with humanity is also a story of illumination. Before oil lamps or candles, the first torches were simple resin-soaked sticks cut from pine or birch. The sticky sap burned bright and long, transforming night into navigable space. Torches guided hunts, lit cave walls where ancient artists painted, and marked pathways through forests. Soot marks found deep within prehistoric caves suggest that humans carried light into darkness, using fire to explore the unknown. Over time, the torch became more than a tool, it became a symbol. Its flame represented enlightenment, courage, and continuity. From processions to rituals, the torch was a portable sun, carried by human hands to defy the night. Yet the evolution of light continued. People soon learned that melted animal fat, placed in shallow stone bowls, could burn with a steady, gentle flame. Plant fibers or moss served as wicks, drawing the liquid upward to sustain the glow. These early lamps, though crude, changed domestic life forever. They illuminated the interiors of caves, homes, and temples, leaving black traces of smoke that still cling to ancient walls. Some were beautifully carved into the shapes of animals or spirits, suggesting that the light they produced was sacred as well as practical. Each small flame represented a piece of the sun, tamed and brought indoors. These early lamps whispered through the dark hours, transforming human nights into times of warmth, story, and reflection. In some places, fire became eternal. In ancient Persia and India, entire temples were built around flames that never went out. Priests tended these sacred fires continuously, feeding them with precise amounts of oil or wood. The flames represented purity, divine truth, and the unbroken connection between the physical and spiritual worlds. Worshippers believed that if the flame died, a cosmic balance would be lost. Some of these eternal fires still burn today, sustained by natural gas vents or centuries of human devotion. Within their light, people saw more than warmth. They saw continuity, belief, and the persistence of life itself. Even as empires rose and fell, those flames burn on, testaments to humanity's reverence for the eternal nature of light. Myths from every culture echo this deep connection. In Greece, the Titan Prometheus stole fire from the gods and gave it to mankind, suffering eternal punishment for his gift. In Polynesian tales, the hero Maui brought fire from the underworld, while in the myths of Native America, animals conspired to steal it for the first people. Across the world, stories of the theft of fire reflect a shared understanding that to possess flame was to share in divine power. Fire was creation and rebellion in one, both a gift and a forbidden fruit. It symbolized knowledge, progress, and the dangerous freedom of choice. Through these myths, humanity expressed an eternal truth, that enlightenment always comes with risk, and that every spark carries the shadow of its source. Long before humans harnessed it, wildfire was part of the planet's natural rhythm. Lightning strikes ignited forests and grasslands, shaping ecosystems through cycles of destruction and renewal. Some seeds even evolved to sprout only after fire, showing that nature itself depends on periodic burning for rebirth. When humans entered this cycle, they learned to respect and adapt it. Ancient people used controlled burns to clear land, promote new growth, and manage hunting grounds. Fire became a tool not only of survival but of stewardship, a force that, when guided with wisdom, sustained rather than destroyed. The mastery of fire thus carried both creative and moral weight. It taught humanity the dual nature of power, to control it without succumbing to it. Charcoal, pottery, metal, glass, torches, lamps, and sacred flames, all trace back to that first moment when an ember was cupped between human hands and kept alive. Each new use of fire deepened our relationship with energy, matter, and imagination. From campfires to kilns, from hearths to foundries, from torches to electric light, every flame lit since then is part of the same lineage, a chain of discovery stretching across millennia. Fire transformed not just how humans lived, but how they thought, how they worshipped, and how they dreamed. It gave rise to the first technologies, the first art, the first myths, and the first understanding that creation requires both discipline and wonder. To this day, every light that burns in the darkness carries within it the memory of that ancient fire, the one that taught humanity how to turn the wild chaos of the world into warmth, shelter, and meaning. Wildfires have always been an essential part of Earth's grand ecological rhythm, shaping the balance between destruction and renewal in ways both visible and invisible. These natural fires, often sparked by lightning, cleared old vegetation, released nutrients, and created open ground for new growth, allowing ecosystems to breathe, evolve, and sustain their diversity. Many plants came to depend entirely on fire, with seeds and cones designed to respond only when heat or smoke touched them, a signal from nature that it was time to begin again. Even the air we breathe today carries traces of ancient fires, the atmosphere subtly altered and enriched by the gases born of flame. Though in the modern world wildfire may appear only as a symbol of devastation, in truth it is a key element in the planet's long-standing design of renewal, ensuring that forests, grasslands, and savannas do not stagnate but continue to thrive through cycles of rebirth. The heat that consumes also nourishes, as fire resets the biological clock of landscapes, rejuvenating the soil and returning balance to systems that would otherwise choke with unchecked growth. Certain plants, such as the mighty giant sequoia of California, the lodgepole pine of North America, and the Australian banksia, embody this paradox most clearly. Their cones remain tightly sealed for years, guarded by resin that only fire can melt. When the forest burns, the intense heat cracks these shells open, releasing seeds into freshly fertilized ash where competition has been cleared away. In the silence that follows the blaze, those seeds find perfect ground to grow, turning ruin into life once more. This ancient partnership between flame and forest is not a tale of destruction but of adaptation, proof that the living world thrives not in spite of fire but because of it. For millions of years, these fiery cycles have sculpted habitats, ensuring renewal and diversity. Without them, the very forests we cherish would grow stagnant and weak. The pine cones that open in the wake of fire, scattering seeds across blackened soil, are small miracles of endurance, nature's testament that life often requires surrender to survive. In the Great Plains and open savannas of Africa, the prairies of North America, and the vast steppes of Eurasia, fire serves yet another vital purpose. Here, periodic burning acts as nature's gardener, pruning away old grasses, removing dead matter, and preventing trees from invading open ground. After every burn, the earth bursts into green, the ash serving as rich fertilizer while sunlight pours unobstructed onto the rejuvenated soil. Grazing animals soon return, feeding on tender shoots that sprout from the blackened earth, beginning a new cycle of life and nourishment. Indigenous peoples across continents long recognized this natural rhythm and learned to use it through controlled burns, maintaining balance and productivity in the land. They understood that without fire, grasslands would gradually transform into forests, losing the species that depend on openness and light. These ancient practices mirror nature's own wisdom, that creation and destruction are twin forces, eternally intertwined. Lightning, the sky's fiery messenger, remains one of the most common sources of natural fire, striking the earth tens of thousands of times each day. Each flash carries immense energy, heating the air to tens of thousands of degrees in an instant. When it meets dry vegetation, it ignites the land, linking atmosphere and earth in a direct, powerful exchange. Most of these fires burn briefly, flickering out as quickly as they begin, but some grow vast enough to reshape entire ecosystems. Today, satellites track these patterns across the globe, revealing a breathtaking dance between weather, vegetation, and fire that has been ongoing since long before humans appeared. What begins as a storm's momentary strike becomes part of a planetary rhythm of energy and renewal, a reminder that even destruction has purpose. When vegetation burns, The organic structures holding life's nutrients, carbon, nitrogen, potassium, calcium, and phosphorus, break down and return to the soil. This release fuels an explosion of fertility after the fire, visible as waves of fresh green blanketing the scorched earth. The ash, far from being lifeless residue, acts as a gentle fertilizer, balancing the soil's acidity and enriching it with minerals. Rain carries these nutrients deep into the ground where microbes, fungi, and roots transform them into food for the next generation of growth. Fire, then, is not an end but a transformation, a grand recycler ensuring that the energy of the past becomes the foundation of the future. Every seedling rising from the ashes carries within it the memory of that fire, a quiet inheritance of resilience. The chemistry of ash plays an even subtler role. Composed of alkaline minerals, it neutralizes acidic soils, creating favorable conditions for new plant life. Mixed with rainwater, it seeps into the soil as a mineral-rich tonic that awakens dormant microorganisms and restores balance. Farmers across ages have echoed this natural process by spreading wood ash on their fields to promote fertility, an act that mimics the cleansing and renewal of wildfires. In forests too acidic for growth, the neutralizing power of ash opens new pathways for roots to take hold, turning devastation into restoration. Even in volcanic regions, where molten earth spews fire and ash across the landscape, the pattern remains the same: destruction followed by renewal, silence followed by bloom. On the blackened forest floor, beneath layers of soot, chemistry and life work hand in hand to heal the land. In this interplay of heat and rebirth lies one of Earth's greatest truths: that fire, for all its fury, is an artist of creation. The influence of fire extends beyond plants and soil, shaping the behavior of animals as well. In parts of Australia and Africa, certain raptors, notably black kites and brown falcons, have been observed engaging in a phenomenon that astonished scientists. These birds, known to indigenous peoples as firehawks, have been seen picking up smoldering sticks from active wildfires and dropping them into unburned grasslands. The resulting new fires drive insects, lizards, and small mammals into the open, where the birds swoop down to hunt them. For centuries, local communities had spoken of these fire-carrying birds, and modern science has since confirmed their extraordinary behavior. This deliberate manipulation of flame marks one of the few known cases of non-human creatures using fire as a tool. The image of a bird wielding a burning branch is both haunting and awe-inspiring, a glimpse into evolution's genius, where instinct and intelligence blur. Here, fire becomes a hunting partner, an active force within the natural strategies of survival. Such interactions reveal that flame is not merely a threat or a gift confined to humanity, but a living element woven through the fabric of life itself. Even among insects, the influence of fire reaches astonishing depths. Certain species of fire beetles, for instance, have evolved the ability to detect infrared radiation, the heat signature of distant fires, from many kilometers away. Instead of fleeing from flame, they fly toward it, seeking the freshly burned forests where they lay their eggs. The charred wood provides an ideal nursery, free of predators and full of nutrients. Their bodies, exquisitely attuned to heat, carry tiny sensors that can detect temperatures far beyond the range of human perception. This adaptation ensures their species thrives in the aftermath of destruction, demonstrating again how life finds opportunity in even the harshest environments. From trees that rely on fire to open their seeds, to birds that wield it as a weapon, to beetles that follow its scent across the horizon, the story of fire in nature is not one of chaos but of interconnection. Every blaze is a moment in an endless symphony of renewal, a testament that the forces of death and creation are inseparable. As flames consume old growth, they make way for new, turning forests into fertile ground, grasslands into oceans of green, and ash into the seedbed of life. It is easy for humans, standing in the face of wildfire's destructive power, to see only loss. Yet from the planet's perspective, fire is not a villain but a caretaker, a sculptor of balance and diversity, a teacher of resilience. Through it, the Earth continually renews itself, ensuring that life, in all its forms, remains dynamic, adaptable, and unending. The larvae feed on weakened trees and charred bark, thriving where other creatures cannot. These beetles are equipped with tiny infrared receptors so sensitive that they can detect temperature changes smaller than a single degree, their ability surpassing many human-made detectors. In a way, they have evolved to follow fire as others follow water or light, ensuring their survival in an environment shaped by periodic burning. This strange attraction to heat shows how deeply fire is woven into the fabric of life, guiding even the smallest creatures through cycles of destruction and renewal. Fire changes landscapes faster than erosion or rain. While wind and water slowly shape the surface of the earth, fire works in moments, its blazes capable of altering entire ecosystems, stripping vegetation, exposing soil, and changing the chemistry of both air and ground. Hillsides blacken, forests open, and new patterns of life emerge within days. In some cases, repeated burning over centuries creates permanent biomes like savannas and shrublands, showing that the rapid transformation caused by fire rivals geological forces in its impact, yet operates on a human timescale. Afterward, the land never returns to what it once was but becomes something new, shaped by both loss and potential. The speed of this process reveals how energy can remake the planet, reminding us that change need not be slow to be profound. Fire is Earth's sudden sculptor, carving renewal out of devastation. In deserts, small fires maintain balance. Though rare, these blazes are vital when they do occur, as the sparse vegetation, scattered shrubs and hardy grasses, burns in brief flashes that clear dead material and stimulate new shoots. These small fires recycle nutrients into thin desert soils, allowing life to persist in what seems barren. Many desert plants have thick bark, waxy coatings, or seeds resistant to heat, ensuring they survive and regenerate swiftly afterward. Animals have evolved in step, burrowing underground or hiding in rocky shelters until the land cools again. By removing old growth and stimulating new life, fire prevents competition for limited water and sunlight. Without it, deserts could choke in their own dryness. Even in these fragile ecosystems, fire acts as a quiet gardener, maintaining balance through renewal. Charred forests, too, serve a purpose beyond destruction. After a wildfire, the blackened remains of trees cool the soil and trap moisture, the dark carbon residue forming a layer that absorbs rainfall and holds it in place. Beneath this burnt blanket, roots, seeds, and microorganisms find refuge, insulated from the harsh sun. The burned wood acts as a sponge, slowing evaporation and preserving moisture for the first stages of regrowth. Soon, mosses and fungi colonize the cooled earth, beginning the slow return of life. Scientists studying post-fire ecosystems have found that soil beneath the charred surface often holds more water than unburned ground. This paradox, where destruction creates conditions for recovery, reveals that a blackened forest floor, though seemingly dead, hides a pulse of renewal waiting for rain and light to awaken it. Fire also shapes migration paths of animals across continents. For countless species, the presence of fire determines when and where they move. Grazing animals follow the tender green shoots that sprout after burns, finding nourishment in the renewal, while birds of prey and scavengers gather at fire edges to hunt insects and animals fleeing the heat. Even massive migrations in Africa and Australia follow seasonal burn patterns, moving with the cycles of flame and regrowth. Over time, these patterns carve invisible trails across the land, guiding herds and predators alike. Fire becomes a map written in light and ash, directing life towards sustenance, a force of guidance as much as destruction. When the flames fade, life begins anew, tracing paths first drawn by ancient fires across open plains. Even smoke plays a part in this grand cycle. When plumes rise, they release microscopic ash and carbon particles that drift into the sky and act as condensation nuclei, giving water vapor something to cling to. Clouds form around them, sometimes thickening into storms that release rain. Some regions even experience increased rainfall downwind of large fires as smoke changes how sunlight and heat interact with the atmosphere. Yet the balance remains fragile. Too much smoke can block sunlight, cooling the air and halting cloud formation. Scientists study these delicate interactions to understand how fire influences climate patterns on both local and global scales. What rises as destruction can return as a gift, as rain falls back upon the scorched earth that gave it birth. Among the ashes, life stirs in unlikely forms. Certain fungi thrive only on burned ground. Their spores may lie dormant for decades, awaiting the heat and chemical shift of fire to awaken them. Once the ground cools, they spring up swiftly, sending forth fruiting bodies that feed on charred remains, breaking down carbonized material and returning nutrients to the soil. Some, like morel mushrooms, even form symbiotic relationships with burned trees, flourishing where life seems to have ended. For foragers, their appearance is a sign that renewal has begun. Fire clears the surface, but below, fungi rewrite the soil's chemistry, transforming destruction into fertile potential. Long before human settlement, prairie fires once stretched across thousands of miles. In the vast grasslands of ancient North America, lightning and dry winds would ignite immense fires that rolled for weeks. Yet these flames did not destroy, they renewed. The grasses evolved deep roots that survived below the heat, and within days, tender shoots re-emerged. Bison, antelope, and countless other species followed, feeding on the fresh growth. Smoke from those ancient blazes rose to the horizon, marking the endless cycle of rebirth that defined the prairie's life. Indigenous peoples observed and honored this rhythm, using controlled burns to mimic nature's own balance, maintaining abundance and harmony. Though the modern landscape is quieter, its soil still carries the memory of those fires, the echo of flame that once brushed continents in gold and smoke. In tropical savannas, fire's role is even more essential. The mix of grass, trees, and seasonal rain forms ecosystems dependent on frequent burning. Savannas do not perish in flame, they are reborn by it. Grasses regrow within days, nourished by ash and open sunlight, while thick-barked trees survive to sprout anew. Fire prevents dense forests from forming, keeping the plains open for elephants, lions, and vast herds of antelope. Without regular burning, these ecosystems would change entirely, losing their defining identity. Scientists have found that even lightning alone can maintain this equilibrium, shaping life through time. Fire serves as both boundary and sculptor, preserving openness where forests might close, maintaining breadth and space in the land's design. Each flicker across the horizon is a quiet collaboration between earth, rain, and flame, an eternal partnership ensuring life continues to renew itself. Millions of years ago, lightning fires may have birthed the first grasslands. As the planet's climate dried, lightning struck wooded plains more often, clearing trees and leaving behind open spaces where grasses thrived. These ancient burn zones became the cradles of today's savannas, prairies, and steppes, ecosystems that still define much of Earth's surface. Animals evolved alongside these fires, their lives synchronized with the rhythm of burning, grazing, and migration. Fossilized soils reveal layers of charcoal marking this transition, proof that fire acted not only as destroyer but as architect, shaping the balance between forest and open plain, shadow and light. Even now, traces of ancient blazes lie buried beneath our feet, reminders of the fire's role in sculpting life's path. Charcoal left from old wildfires plays a long game. It can store carbon in the soil for centuries. When wood burns incompletely, it becomes charcoal, a stable form of carbon that resists decay. Instead of releasing carbon back into the atmosphere, this biochar locks it away, enriching soil fertility while helping moderate climate by keeping carbon out of circulation. Thus, even in death, fire continues to nourish and protect. Across deserts, forests, prairies, and savannas, fire remains both destroyer and creator, a paradoxical heartbeat of the earth, teaching that endings and beginnings are often the same flame viewed from opposite sides of time. Forest floors across the world hold vast stores of ancient charcoal, silent archives of countless fires that have burned through the ages, each layer a geological memory of transformation and survival. These deposits, often buried beneath thick layers of soil, still influence the chemistry of the earth today. The carbon locked within them interacts subtly with minerals, microorganisms, and plant roots, shaping the fertility and balance of ecosystems long after the flames have died. In recent years, scientists have begun deliberately recreating this natural process through controlled burns to produce biochar, an echo of nature's method for sustainable agriculture and carbon sequestration. What began as a natural accident millions of years ago has become a human endeavor to restore equilibrium. Each layer of charcoal beneath our feet is a silent reminder that even what remains after destruction can serve as a source of renewal, storing both memory and potential life within the soil itself. Fire, in this way, acts as both destroyer and creator in every ecosystem. Nowhere in nature is duality more vividly displayed than in the behavior of flame. It consumes yet renews, it clears yet nourishes. In forests, prairies, deserts, and wetlands alike, the same process that devastates one generation prepares the ground for the next. Seeds that require heat to open, fungi that thrive on charred remains, and animals that follow the regrowth all depend on what first appears to be ruin. Without fire, ecosystems stagnate and overgrow, losing vitality and balance. With it, the cycle of rejuvenation continues. Each blaze mirrors creation itself, where endings and beginnings coexist within the same flicker of light. Scientists studying fire ecology have discovered that even the timing and intensity of natural burns are tuned by evolution. The element that once terrified early humanity is now revealed as one of the planet's oldest tools for balance, shaping the renewal of life with every spark that meets the air. Fire, at its core, requires three elements: heat, fuel, and oxygen, a perfect trinity known as the fire triangle. Every flame, from the smallest candle to the mightiest inferno, exists only when these three forces work together in harmony. Heat initiates the reaction, fuel sustains it, and oxygen keeps it alive. Remove any one, and the flame collapses instantly. This principle explains why damp wood smolders instead of burning, why a blanket or foam can extinguish flames, and why controlled fires can be carefully maintained within engines, furnaces, or even the delicate circuits of rocket propulsion. The fire triangle is both a symbol of chemistry and a metaphor for balance. Too much of one element leads to chaos. Too little leads to failure. Humanity's earliest experiments with combustion, rubbing sticks, striking flint, tending embers, were acts of understanding this hidden equilibrium. Every spark obeys it, from the campfire's orange glow to the distant blue blaze of a star, which burns through its own version of this eternal equation. Fire, in all forms, is the art of balance sustained through chemistry. Its fragility hides beneath the illusion of power, for it depends entirely on circumstance. The moment one component, heat, fuel, or oxygen, is removed, the process ends. If heat drops below ignition temperature, the reaction ceases. If the fuel runs out, nothing remains to burn. If oxygen is cut off, the chemical chain collapses. Firefighting itself is built on this principle. Water cools, foam smothers, isolation deprives fuel. The instant one side of the triangle disappears, so too does the flame. To extinguish fire is not to destroy it, but to unmake the circumstances that sustain it. A profound reminder that even the fiercest forces of nature vanish when their balance is broken. Some chemical reactions mimic fire without producing flame, existing instead as slow, invisible counterparts to combustion. Rusting iron, for instance, follows the same principles of oxidation that govern burning but at an imperceptible pace. When iron rusts, its atoms bond slowly with oxygen and moisture, releasing energy too gradually for light or heat to appear. Over time, metal transforms into reddish oxide, a solid, silent version of combustion stretched across years instead of seconds. This process reveals that rust and flame are merely points along the same continuum of chemistry, separated only by speed. The quiet decay of metal shares its essence with the brilliance of a blaze, both representing matter's attempt to reach equilibrium. This slow fire has shaped civilizations, eroding ships, bridges, and machines, carving human industry back into dust. In both rust and flame, matter releases stored energy until stability returns, proving that even in stillness, the fire's spirit endures. Yet not all fires are born of destruction. Some reactions release energy as light but not as heat. These are phosphorescent or chemiluminescent reactions, nature's peaceful fires. In certain minerals, marine organisms, and laboratory reactions, light emerges from transformation without burning. Fireflies, for example, glow through a precise chemical dance that produces light with almost no wasted heat, a pure and efficient form of illumination. Deep in the ocean, bioluminescent creatures communicate and hunt using this cold fire, painting the abyss with constellations of green and blue. These reactions, studied by scientists for applications in medicine, imaging, and clean lighting, reveal that combustion is not the only way for matter to shine. Phosphorescence embodies a quiet radiance, a fire that does not consume, a symbol of light without loss. It shows that transformation can be gentle, that illumination need not destroy. Beyond these gentle glows lies the wild chemistry of elements more reactive than oxygen. Fluorine, the most reactive element known, can produce combustion far more violent than any fire familiar to Earth's surface. When fluorine acts as an oxidizer, almost any material, even glass or sand, can ignite. The reaction releases staggering amounts of energy, accompanied by bursts of blinding light and clouds of corrosive gas. Fluorine's eagerness to bond rips atoms apart, and scientists handle it only in sealed, controlled environments. Theoretical propulsion systems imagine fluorine as an oxidizer far more powerful than oxygen, capable of fueling rockets beyond current limits. Yet its volatility makes it impractical for most uses, serving instead as a reminder of the outer limits of combustion chemistry, a fire so fierce that it transcends flame, existing purely as reaction, the raw expression of matter's drive to combine. In contrast, hydrogen burns with one of the gentlest flames in nature, nearly invisible to the human eye. When hydrogen reacts with oxygen, it produces water vapor and releases heat, yet emits almost no color or smoke. The faint blue hue that appears comes from excited molecules releasing photons as they cool. Because hydrogen fires are so clean and faint, they are difficult to detect, requiring specialized sensors for safety. Despite this, hydrogen is hailed as a fuel of the future, abundant, efficient, and clean, producing only water as a byproduct. Its ghostly flame embodies purity and power, showing humanity's potential to harness energy without pollution. Where other fuels leave ash and soot, hydrogen leaves only vapor, an elegant echo of the planet's original chemistry, when sunlight and gas first gave birth to stars. Even ordinary materials reveal strange behavior when exposed to fire's extremes. Liquid oxygen, for instance, can make organic materials explode on contact. When substances like paper, fabric, or oil absorb liquid oxygen, they become saturated with one of the most reactive elements in existence. A single spark or frictional heat can trigger violent combustion. This reaction reminds us that the line between creation and destruction is razor thin, that fire's essence resides not in destruction itself, but in the energy locked between atoms waiting to be released. From ancient forest floors lined with charcoal to futuristic fuels that burn invisibly clean, fire remains the eternal link between matter and energy, decay and renewal. It consumes and creates in equal measure, its chemistry weaving through every scale of existence, from the rusting of a nail to the burning heart of a star. Thus, the story of fire is the story of balance. It is the dialogue between chaos and order, between energy's hunger and nature's restraint. It teaches that destruction and creation are not opposites but companions, two halves of the same process that keeps the world alive. Beneath our feet, in the ancient layers of charcoal, lies the proof that even what was burned and broken continues to nourish the living. Fire reminds us that change, no matter how fierce, can carry the seed of renewal. Its light may flicker, fade, and vanish, but its memory endures, in the soil, in the stars, and in the pulse of life itself. ChatGPT. If these oxygen-rich materials are disturbed, even a small spark or a brush of friction can unleash a violent explosion. The reason lies in chemistry itself. Oxygen fuels combustion so intensely that energy releases in a fraction of a second, a burst of transformation too fast for the eye to follow. Engineers who work with rocket propellants and cryogenic systems must take extraordinary precautions to prevent such contact, for liquid oxygen, while essential to space flight, turns ordinary matter into potential fuel, waiting only for a trigger. In rockets, it serves as the oxidizer that allows engines to burn at unimaginable temperatures, propelling spacecraft beyond the atmosphere. But outside those systems, its touch can transform paper, oil, or cloth into instant fire. This duality between usefulness and danger defines the very essence of fire, It is creation and catastrophe, beauty and peril, held in fragile balance. Among the many wonders of combustion, few are as visually striking as the way sodium burns. When heated, sodium atoms absorb energy, causing their electrons to jump to higher states before falling back again, each fall releasing light at a precise wavelength that shines as deep golden yellow. This distinctive glow, one of chemistry's most recognizable signatures, illuminates street lamps, fireworks, and even the tiniest traces of sodium vapor in a laboratory flame. Long before modern spectroscopy, scientists learned to identify elements by these colors, using fire itself as a tool to read the atomic language of the universe. Within the apparent chaos of flame lies perfect order. Each hue corresponds to exact transitions of energy within atoms, a delicate dance of electrons that converts invisible processes into radiant light. The warm glow of sodium, like the structured patterns of stars, proves that the universe is governed by harmony, even in the heart of destruction. Other metals, too, speak in their own colors. Strontium paints the night sky crimson, barium glows green, copper burns blue, and sodium adds its golden tones. These are the colors of fireworks, chemistry transformed into spectacle. Fireworks are precision-engineered explosions of powdered science. Inside every shell lies a miniature laboratory of fuel, oxidizer, and metal salts carefully arranged to control timing, altitude, and hue. When ignited, the fuse triggers a chain of reactions, first lifting the shell skyward, then bursting it open at a calculated height to scatter burning stars across the sky. The shape of each bloom, the duration of its shimmer, and even the sound of the explosion are engineered with mathematical precision. The result is a fleeting masterpiece where chemistry, physics, and artistry converge. The colors we admire are the product of oxidation and reduction reactions happening in milliseconds, each photon of light a signature of atoms returning to balance. Fireworks are humanity's most poetic collaboration with chemistry, brief, breathtaking, and born entirely from understanding how to tame fire's chaotic heart. Their beauty endures only moments, yet each burst reminds us that knowledge, art, and nature can merge perfectly in light. If fireworks are fire's grand symphony, a candle flame is its quiet sonata. To the naked eye, a candle appears steady, calm, and continuous, yet under high-speed photography, it reveals itself as a storm of microscopic explosions. Every second, countless carbon particles ignite, flare, and vanish, releasing bursts of heat and light in a rhythm too fast to hear. These miniature detonations form the shimmering we perceive as the flicker of a flame. Within that soft glow, molecules are constantly forming and breaking apart in perfect chemical choreography. What seems serene is, in truth, ceaseless motion, a balanced storm sustained by chemistry's most elegant laws. Each atom dances between transformation and stillness, forming the delicate boundary between light and shadow. The candle, a symbol of peace and thought, hides within it the restless soul of fire itself. The black soot it sometimes leaves behind is a trace of imbalance, a sign that the flame lacked enough oxygen for perfect combustion. Incomplete burning leaves behind tiny carbon grains that rise glowing orange before cooling into black smoke. These specks, microscopic but powerful, are the story of flames struggling for breath. In ancient times, soot collected on the ceilings of caves and temples, silent evidence of early humans' intimacy with fire. Later, artists ground it into ink and paint, turning waste into beauty. Even now, soot tells a story about air, heat, and harmony. Scientists study it to make engines cleaner and combustion more efficient. Each particle is a fragment of unfulfilled potential, proof that perfection in nature requires balance between fuel, heat, and air. Every flame carries within its shape the signature of its energy. A narrow, steady flame shows slow, clean burning, while wide, jagged edges reveal turbulence and speed. The flame is a living graph of reaction, its curves and motion encoding molecular velocities, airflows, and pressure. Scientists read these shapes as language, each flicker a piece of data in the chemistry of light. Even the subtlest change in air humidity or temperature can reshape a flame, transforming it from slender elegance to roaring turbulence. To the human eye, it's beauty; to science, it's information. Every flicker we see is an expression of balance between reaction speed and heat transfer, a fleeting portrait of matter transforming into energy. On Earth, flames stretch upward as hot gases rise and cool air sinks, but in the weightlessness of space, fire behaves in an entirely different way. Without gravity, the familiar teardrop shape disappears, replaced by a perfect glowing sphere suspended in air. These spherical flames, studied by astronauts aboard space stations, burn quietly and evenly, sustained only by the slow diffusion of oxygen. They emit steady light without flicker or turbulence, behaving like miniature suns. In this microgravity environment, combustion becomes almost silent, a chemical meditation. The absence of convection reveals how fire truly works at its core, without the interference of rising heat or falling air. These weightless flames burn cooler and more efficiently, offering valuable insight for designing cleaner engines and safer fuels. Watching a spherical flame drift in space feels like witnessing the universe's most primal art form, light born purely from chemistry, untouched by gravity or chaos. In that suspended orb of fire, scientists glimpse the essence of balance itself, where matter and energy meet in perfect symmetry. Through all these forms, from the furious explosions of liquid oxygen to the golden shimmer of sodium, from the thunder of fireworks to the whisper of a candle's glow, fire remains one of nature's greatest paradoxes. It destroys yet creates. It consumes yet illuminates. It is both danger and discovery, a symbol of the fragile equilibrium that defines existence. Every spark, no matter how small, contains within it the same laws that power the stars. The chemistry that drives a flickering candle is the same that fuels supernovae billions of light years away. Across every scale, fire is balance in motion, an eternal dance of atoms seeking peace through transformation. When confined in microgravity, fire reveals a side of itself unseen on Earth. Without the upward pull of gravity, there is no convection, no rising of hot air or falling of cool gas, and so flames become slow, smooth, and symmetrical. Researchers studying these spherical flames in the weightless environment of space can observe combustion in exquisite detail, watching the gradual diffusion of oxygen and fuel mix like slow-moving currents of light. The absence of turbulence allows scientists to see how reactions truly propagate, molecule by molecule, as if time itself had been slowed. These experiments are far from academic. They help engineers design safer spacecraft, more efficient engines, and cleaner methods of burning fuel on Earth. When convection is stripped away, only molecular diffusion remains to feed the flame, producing the purest version of combustion, a perfect balance between chemistry and physics. In the serene glow of a spherical flame, one can glimpse the very foundation of energy itself, the same processes that govern the stars, drive engines, and flicker in a humble candle's flame. Yet fire, for all its simplicity, is filled with surprises. Under extreme conditions, even gases that we think of as extinguishers can become part of combustion. Carbon dioxide, which normally snuffs out flame by depriving it of oxygen, behaves differently when subjected to immense pressure and heat. In experimental chambers replicating the interiors of planets or high-energy industrial systems, scientists have found that carbon dioxide can decompose, releasing oxygen atoms that sustain brief, faint flashes of combustion. These events, fleeting and rare, reveal that even the most stable molecules hold hidden potential when pushed to their limits. What we once considered inert may, under other skies or in alien atmospheres, become reactive and alive with energy. Understanding these reactions helps scientists predict atmospheric behavior on distant worlds where pressures and temperatures exceed anything earthly, showing that fire is not a fixed phenomenon, it is a response, a dialogue between matter and environment, always changing its form. Within this deep language of physics, no element is ever truly dormant. Each only awaits the right combination of forces to awaken. Fire also speaks through electricity. Within the glowing air of a flame, gas molecules break apart into ions and electrons, charged particles that can move in response to electric fields. When scientists apply a current to a flame, these particles accelerate, creating what is called an ionic wind, a faint but measurable thrust. This gentle push can move objects lighter than a feather or drive air through microengines. The same principle powers ion thrusters in spacecraft, where electrically charged gases are expelled to produce smooth, continuous propulsion across the vacuum of space. In the laboratory, electric fields can even bend or shape flames, guiding them like threads of light. Each flicker becomes not just a chemical event but an electrical one, a meeting of heat, charge, and motion that bridges the worlds of combustion and plasma physics. Invisible yet powerful, these small forces reveal that fire is more than warmth and glow. It is motion made visible, a living plasma that hints at future technologies still waiting to be discovered. But not all flames roar or blaze. Some whisper. These are the cold flames, nearly invisible, ghostly blue, and so gentle that they can be touched briefly without harm. Unlike the fierce fires of daily life, cold flames occur when fuel and oxygen react slowly, releasing energy at low temperatures that never reach the threshold of full ignition. Their existence defied expectation. For centuries, scientists believed combustion could not occur without heat, until these quiet reactions proved otherwise. They burn silently in certain engines and chemical reactors, often as a prelude to ignition, revealing the subtle pathways that lead from dormancy to flame. Because cold flames consume fuel efficiently and emit little soot or pollutant, studying them offers hope for cleaner, more sustainable energy. They demonstrate that transformation need not always be violent. Chemistry can whisper as well as roar, showing that even at the edge of visibility, fire continues to write its story of change. Fire's transformative power does not stop at gases and flames. It can reshape the very earth itself. When exposed to intense heat, ordinary sand melts into glassy stone known as vitrified rock. This phenomenon occurs naturally when lightning strikes the ground or when lava flows across sandy plains, but humans have also reproduced it in furnaces, explosions, and ancient fortifications. Archaeologists have discovered vitrified walls in the ruins of European fortresses, their stones fused together by deliberate burning, perhaps for defense or ritual. Once cooled, the material hardens into a glossy, erosion-resistant shell, preserving the mark of heat for millennia. Modern science uses similar processes to create synthetic stone for construction or to seal hazardous waste in durable glass-like casings. Every piece of vitrified rock is a story frozen in time, a moment when Earth turned liquid and then solid again, capturing the memory of transformation. Lightning, nature's own fire, takes this process further still. When a bolt strikes the ground, temperatures soar higher than the surface of the sun for an instant. The sand beneath melts and fuses into branching, glassy tubes called fulgurites, delicate sculptures of energy frozen in place. Within their walls, iron-bearing minerals align along the lightning's electric path, recording magnetic traces of the strike. By studying these magnetic signatures, scientists can reconstruct the direction and strength of ancient storms, reading the history of thunder written in stone. Each fulgurite is a physical echo of the meeting between sky and earth, a moment when power beyond measure flowed into matter and left its silent mark. To hold one is to touch the residue of an event that existed for less than a heartbeat but burned hotter than any human flame. Beyond Earth, fire continues its endless variations. The stars themselves are cosmic furnaces, not fueled by oxygen but by fusion. Deep in their cores, under crushing gravity, hydrogen atoms merge into helium, releasing immense energy as light and heat. This process, nuclear fusion, is the purest and most powerful fire in existence, the engine that drives the universe. It is the same energy humans attempt to harness in experimental reactors, hoping one day to replicate the sun's efficiency and create clean, limitless power. Every sunrise on Earth is a reminder of this distant blaze, of a cosmic fire that sustains life across space and time. While terrestrial flames rearrange molecules, stellar fires remake atoms themselves, binding and unbinding matter on a scale beyond comprehension. The glow of a candle or the flash of lightning are reflections of this same universal language of transformation, a quiet echo of the nuclear symphony playing across the stars. Yet even in the vastness of the cosmos, fire remains governed by balance. On Saturn's moon Titan, rivers and lakes of liquid methane flow under orange skies. The air is thick with hydrocarbons, fuel in its rawest form, but the absence of oxygen keeps the world calm and still. If a single spark were introduced with oxygen present, the entire landscape could ignite in a storm of flame. Titan is a paradox, a planet that rains fuel but never burns. Scientists study it to understand how chemical potential behaves without reaction, how fire's possibility can exist perpetually unfulfilled. Its frozen lakes and hazy skies mirror the delicate equilibrium between what could burn and what does not, showing that fire is not universal but conditional, dependent on the fragile meeting of fuel, oxygen, and the right spark. Elsewhere in the solar system, fire takes stranger forms. On Io, one of Jupiter's moons, volcanoes erupt in sulfur flames that paint the landscape in yellows and blues, glowing against the blackness of space. These eruptions are driven not by sunlight or atmosphere but by tidal forces, Jupiter's immense gravity kneading Io's interior, generating heat from friction. When sulfur gas escapes and ignites, it produces plumes that rise hundreds of kilometers high, luminous and alien. Spacecraft images reveal fountains of molten material, glowing like torches in the void. Io's surface is constantly renewed by these sulfurous blazes, making it the most volcanically active world known. Watching these distant eruptions feels like witnessing the birth of planets, a reminder that fire is not confined to Earth's forests or furnaces but burns wherever energy and chemistry meet, in languages the human eye is only beginning to learn. At the heart of our solar system, the Sun's corona, a faint halo visible during eclipses, burns millions of degrees hotter than the surface below. Its heat defies logic, farther from the core, yet infinitely hotter. Scientists believe magnetic waves carry energy outward, snapping and twisting like invisible flames in plasma. This outer fire shapes the solar wind, the constant flow of charged particles that bathes the planets, influences auroras, and even affects Earth's climate. The corona's searing light is both mystery and message, a symbol of how energy can move in forms we do not yet fully understand. Whether in a laboratory flame, a glass tube of lightning, or the living fire of stars, combustion remains the same essential act, matter yielding to transformation, energy awakening from rest. Fire connects everything, from the chemical spark that sustains a candle to the nuclear inferno that illuminates galaxies. It is both destroyer and creator, revealing that all change, whether in air or cosmos, begins as a flicker of possibility. When confined in microgravity, the absence of upward flow allows researchers to observe combustion in slow motion, exposing the intricate details of how gases mix and reactions propagate. By studying spherical flames, scientists can model how fire travels through different materials and environments on Earth, improving spacecraft safety while guiding advances in energy efficiency, engine design, and pollution control. The even, serene burn of a spherical flame reveals what happens when convection disappears, and only molecular diffusion carries oxygen to fuel. It is the purest form of fire, stripped of turbulence and chaos, a quiet window into chemistry's true nature. Observing its smooth glow, researchers glimpse the fundamental language of combustion, the same processes that shape the flicker of a candle, the ignition within engines, and even the radiant energy of stars. Under high pressure and heat, even carbon dioxide, the very gas that extinguishes flames under normal conditions, can reveal a hidden side. Usually known for smothering fire by displacing oxygen, carbon dioxide, when pushed to its limits, breaks apart and releases oxygen atoms that briefly sustain combustion. These rare reactions occur under conditions like those deep within planets, or in high-energy industrial environments. The discovery challenges the notion of carbon dioxide as inert, proving that even the most stable compounds possess latent energy waiting for the right conditions to awaken. In the vast language of physics, no element truly rests, every atom waits for a chance to transform. Within flames, gases break into charged particles, ions and electrons, that respond to electric fields, allowing fire to act as a tiny ion engine. When a current is applied, these particles accelerate, creating a faint but measurable thrust called ionic wind. This subtle motion can move objects lighter than a feather or drive microengines, and the same principle underlies certain spacecraft propulsion systems that expel ionized gases for steady motion through space. In laboratories, Electric fields can even shape or bend flames, steering them like threads of light. Each flicker becomes both a chemical reaction and an electrical event, a bridge between heat and motion, showing that fire is not just light or warmth but a plasma in motion, capable of carrying energy and exerting force. Cold flames, on the other hand, tell a gentler story. These rare, faintly blue fires burn slowly and silently at low temperatures, sometimes cool enough to touch. They occur when fuel and oxygen react so gradually that the temperature never reaches normal ignition levels. Nearly invisible and emitting little heat, they nonetheless represent true combustion, proof that fire can exist without roar or glare. Scientists study cold flames to understand the early stages of ignition, to make engines more efficient, and to minimize pollution. They reveal that transformation need not be violent. It can unfold softly, molecule by molecule, whispering rather than blazing. The discovery of cold flames reminds us that energy can move even in stillness, that change can be delicate yet powerful. When heat climbs to the extreme, it can turn sand into stone. Fire so intense that it melts sand and soil forms a glass-like material known as vitrified rock, a transformation seen where lightning strikes, volcanoes erupt, or ancient fortresses burned. Archaeologists have uncovered vitrified walls across Europe, their stones fused by deliberate or accidental fires thousands of years ago. The resulting glassy surfaces resist erosion, enduring as permanent memories of heat. Today, scientists use similar processes to create synthetic stone for construction and waste containment. Each vitrified fragment is a frozen moment of transformation, raw earth turned liquid, then hardened by time into a relic of flame. When lightning strikes the ground, its heat exceeds the surface of the sun for an instant, melting soil into hollow, glassy tubes called fulgurites. Inside these fragile sculptures, iron-bearing minerals align with the electric field of the lightning bolt, locking in faint magnetic traces that preserve the direction and strength of the ancient strike. Studying fulgurites lets scientists read the magnetic history of storms long past. Each one is a captured path of energy, a tangible bridge between sky and earth. To hold one is to touch the residue of a moment too fast and fierce for the human eye, a glimpse of lightning's artistry, of fire sculpting the ground itself. On a far greater scale, stars burn not through chemical combustion but through nuclear fusion. Deep within their cores, gravity compresses hydrogen atoms until they merge into helium, releasing unimaginable energy as light. This is the ultimate fire, the same process that humanity seeks to replicate in fusion reactors on Earth. Fire on our planet rearranges molecules, but stellar fire reshapes atoms themselves. Every sunrise is a gift of fusion, a constant, cosmic combustion that powers all life. The gentle light of a candle or the fierce blaze of a star follows the same laws, matter transforming into energy, heat giving birth to radiance. In distant corners of the solar system, other worlds carry their own strange relationships with fire. Saturn's moon Titan, for instance, rains liquid methane beneath orange skies, its rivers and lakes filled with hydrocarbons instead of water. If oxygen ever reached its atmosphere, one spark could ignite the entire world, transforming it into a global inferno. Yet in its current state, Titan remains calm, a world that rains fuel but never burns. Scientists study such paradoxes to understand how planetary atmospheres balance chemistry and stability. Titan's silent potential reminds us that fire is not universal, it is a delicate harmony between elements, waiting for the right breath of air. Beyond Titan lies Io, Jupiter's volcanic moon, where fire erupts in alien colors. Tidal forces from Jupiter stretch and knead Io's crust, generating heat that fuels immense eruptions of molten sulfur, glowing yellow and blue in the darkness of space. These eruptions can rise hundreds of kilometers high, painting the frozen void with eerie light. Io is the most volcanically active body in the solar system, a living testament to how fire can exist without air, driven by gravity and chemistry alone. Watching these distant plumes is like seeing creation in another language, a reminder that fire's essence transcends planets and atmospheres. Even our sun holds mysteries of flame and plasma in its outermost layer, the corona. Though farther from the solar core, the corona burns millions of degrees hotter than the surface below. Scientists believe that magnetic fields twist and snap there, releasing immense bursts of energy that heat the gas to unimaginable temperatures. From this halo flows the solar wind, a constant stream of charged particles that stretches across the solar system, shaping planetary atmospheres and painting Earth's skies with the auroras. The corona is a fire beyond fire, invisible most of the time yet touching every living atom on Earth. To see it is to glimpse the boundary between matter and energy, where the sun whispers its light across space. Sometimes, that cosmic energy falls to Earth in sudden bursts. When a meteor enters the atmosphere, it compresses the air in front of it so violently that the heat can ignite forests before the rock even touches the ground. Even when the meteor vaporizes completely, the blast of superheated air can spark wildfires across vast regions. Evidence of such events lies buried in ancient layers of charcoal, marking impact moments that reshaped Earth's ecosystems. The Tunguska explosion in Siberia, for example, flattened thousands of trees without leaving a crater, a fiery wave sweeping across the wilderness. Fire from the sky has shaped Earth's history as much as rain and ice have, linking the heavens to the forests below. In the greater reaches of space, enormous clouds of gas and dust, nebulas, glow with soft radiance. Though far too cold for chemical combustion, they shine through ionization. Ultraviolet light from nearby stars energizes their atoms, causing them to release photons in hues of red, green, and violet. Each nebula is like a vast cold flame, fire without heat, light without burning. Within them, stars and planets are born, sculpted by gravity and time. To gaze upon a nebula is to watch creation unfold, the universe painting itself with its own chemistry. Light that has traveled for thousands of years reaches us as a quiet echo of that process, a fire too immense to touch but eternally visible. Fire, both earthly and cosmic, shapes the journeys of worlds and machines alike. When a spacecraft re-enters Earth's atmosphere, it races through the air so fast that gases compress and heat into plasma, wrapping the craft in a sheath of white-hot fire. What we see blazing across the sky is not fuel burning but air itself radiating under extreme energy. Heat shields protect the vessel by absorbing and shedding the heat in layers, a conversation between human design and natural physics. Each descent through this fiery baptism mirrors a meteor's fall but is guided by intention rather than chance. Every return from space is a rebirth through flame, a reminder that motion itself can become light. On a smaller scale, plasma arcs on Earth, lightning bolts, are miniature versions of the solar flares that erupt from the sun. Each bolt is a sudden burst of plasma where air becomes electrically charged, glowing as electrons leap between atoms. Temperatures soar higher than the sun's surface, and the branching veins of light trace patterns shaped by electric fields, much like the magnetic loops that twist across solar storms. To watch lightning is to glimpse the same cosmic forces that rule the stars, condensed into a flash that bridges cloud and earth. Every strike is a heartbeat of the sky, a pulse of the same energy that fuels suns and galaxies. In truth, every fire on Earth, from the smallest match to the largest inferno, carries the memory of stars. The carbon, hydrogen, and oxygen that sustain our flames were forged in stellar cores billions of years ago and scattered through space when those stars exploded. Each spark continues that cosmic story, the transformation of matter into energy, born in the hearts of suns long gone. To light a candle is to hold the universe in miniature, to touch energy that once burned among the stars. Fire is not just a human discovery but a cosmic inheritance, a thread connecting life to the origins of everything. And as that light flickers and fades, the mind softens with it. The warmth settles into stillness, the breath deepens, and thought drifts like smoke into the quiet beyond. Every flame teaches the same truth: nothing truly ends, it only changes form. The fire that warms, that destroys, that illuminates, is the same force that shapes worlds and stars, a reminder that transformation is eternal. As the last ember dims, the stars continue their own endless burning, sending their ancient light through the darkness. Somewhere beyond sight, the universe still glows, remembering itself in every spark, every breath, every heartbeat of heat. Fire waits, eternal, patient, watching over all things, ready to rise again whenever creation calls its name.